Welcome all of you. So previously we studied about the basics of p-n junction, like what is p-type material, n-type material, and how p-n junction forms the fundamental part of PV cell, and then what is photovoltaic effect, and what are different types of cells, how we combine them together to form module or panels, and then subsequently arrays. So continuing with that portion, so today we will cover the characteristics of solar cell. So here we will be studying mainly the current and voltage curves or the power and voltage curves, IV curves or PV curves, fill factor, efficiency of solar cell, and then we will look at how we can increase the total power of PV system or a PV array by connecting different cells in series and parallel. What happens? Then different types of solar PV panels. This will be based on the type of material or type of silicon that we use to make panels, like monocrystalline, polycrystalline, or like its amorphous thin film, and finally the components of solar PV module or a panel. So starting with solar cell characteristics, the first one is IV curve, or like the current voltage or power voltage curve. So these solar cell IV characteristic curves, they are typically the graphs of output voltage that we obtain from a PV cell versus the current which is generated for different levels of irradiation and temperature. You know, like how photovoltaic effect works. Okay, a solar cell would be able to generate power using the energy of light, energy of photons. So that conversion of light energy to electrical energy through PV effect or through PV cell, it involves generation of voltage and current, and the factors which govern these two would be the solar radiation, how much radiation we have, and what is the surrounding temperature, because these two parameters affect the current and voltage a lot. And this explains a PV cell or a panel's ability to convert that sunlight into the energy. So on y-axis we have current, on x-axis you have voltage, and this is a typical IV curve for a PV cell. The maximum value of the current that which can be obtained is called as short circuit current. This is the current when we try to like do a short circuit, like two terminals are shorted with each other. So at that point the maximum current can flow through the circuit. And open circuit voltage is the voltage or the maximum voltage which the system has when the terminals or when the circuit is open, when the terminals are not connected to each other. Okay, and somewhere at the middle, like where the curve changes its direction, like this point represents the realistic maximum voltage and realistic maximum current. These values will always be lower than the short circuit current and open circuit voltage, and this point will give us the maximum power point. Okay, so that's the maximum power voltage and maximum power current. So voltage at maximum power, current at maximum power, and MPP is maximum power point. So maximum power point is voltage into current, like VMP into IMP. So based on this IV curve, if we have to draw a PV curve, what we will do, we will just multiply each value of voltage with the corresponding value of current and get a PV curve. So PV curve looks something like this. So the earlier curve, the IV curve is same, and PV curve, where you can see it starts from 0, like when there is no, the voltage is 0, but there is a maximum current, like say short circuit, and when the voltage is maximum to open circuit. So as per the definition which I have already mentioned, open circuit voltage, it is the maximum voltage that a cell or array provides when terminals are not connected to any load. It's an open circuit condition, and this value is much higher than the maximum real or the maximum power voltage, the voltage which can be achieved at the maximum power point. Similarly, short circuit current, it is the maximum current provided by PV cell or array when output connectors are shorted together. So that's a short circuit condition, and this value is much higher than IMP, the value of current at maximum power. Now, if you look at this curve based on the formula P equal to I into V or V into I, why is it lying below this IV curve? There is no like universal rule that it will always be below this. It can even go above this. The positioning of power or voltage curve will depend on the value of voltage. Typically, like for V less than, if it is less than 1 volt, the power curve will generally be lower than the current curve, and if it is greater than 1 volt, the voltage value, the power curve will generally be higher than the current curve. Okay, that's how you can remember this. Now, since this IV characteristics, they would depend on the two parameters, one related to the solar radiation, another is the temperature of the surrounding, and they affect current and voltage respectively. So, accordingly they would affect the power generated from solar cell or solar array. So, based on the literature, this graph shows the effect of radiation first. So, as you can see in the IV curve, as the radiation goes on increasing from say 400 watt per meter square to 1000 watt per meter square, the amount of current that is generated, it goes on increasing significantly, but there is only slight change or slight increase in the voltage, and this is the maximum power line which is going on increasing corresponding to the current value. So, when we look at the PV curve, you can see as the radiation intensity increases, the power voltage curve also picks up at a higher value, and we are able to get more power at higher radiation, right. So, higher irradiations usually increases current and power, and there is only a slight increase in the voltage. Now, if you look at the temperature, as the temperature increases, the voltage decreases, current stays nearly constant. Okay. So, that is why with the decrease in voltage, the power line will also shift towards the left. So, higher temperature decreases both voltage and power. As you increase temperature from 0 to 25 to 50 to 75, it goes on decreasing the voltage significantly, and hence power also decreases significantly, and current changes only slightly. So, why is it happening like this? When there is high radiation, if we have a lot of energy in the photons that is coming with the sunlight, what will happen? It will generate more electron and hole pairs, and that will increase the photocurrent, because current is proportional to the number of charge carriers that are generated in the semiconductor, right. So, with more intensity, more radiation, more electrons and hole pairs would be generated, more photocurrent would be generated, and hence the power will be higher. Whereas, in case of temperature, higher temperature increases the saturation current of the diode, and when that saturation current of diode is increased, it reduces the band gap or the energy gap of the semiconductor, and that is why it reduces the voltage, and hence since current is constant, at reduced voltage we will get reduced power. So, that is how radiation and temperature affects IV and PV curves of different solar cells. Hence, in the definition when we talked about IV curve or the characteristic curves of solar cells, we said it is for a specific radiation and specific temperature, the relation between I and V or P and V. The other performance characteristic is fill factor. After this, we will look at efficiency. So, what is fill factor? It is a key parameter which represents how close a real world solar cell comes to being an ideal electrical source. So, we have a solar cell manufactured by some company, it has some properties, and now when it is installed in a real world, what is its quality or what is its performance close to its ideal rating or ideal value? That is represented by fill factor. So if you look at the IV curve of a typical PV cell, these are the extreme points, short circuit current and open circuit voltage. And this point where the curve changes the slope, it's the maximum power point. So the maximum power is maximum voltage and maximum current, right, at that maximum power point. And fill factor is, it is the ratio of maximum power upon the theoretical maximum power. Okay, so it is the ratio of maximum power a solar cell can actually provide, that is the MPP point. This is the maximum power which that solar cell can provide in a real world. And VOC into ISC, these are the conditions which are never achieved. So that's the theoretical power it would provide if it is operated at its peak voltage and current simultaneously. So maximum power by theoretical power, the ratio of these two terms determines the fill factor. And if we have to represent it using the area of rectangles shown here, it will be simply the area of smaller rectangle by the area of larger rectangle. So P fill factor is always going to be less than 1, because this point it will never reach here, like at the intersection of VOC and ISC. So it will always be on left hand side of this maximum power point, which is a theoretical maximum power point, but this realistic maximum power point will always be on the left hand side. So the fill factor value is always going to be less than 1. But higher fill factor would mean better efficiency and higher quality of solar cell. Most of the commercial silicon based solar cells, they will have the fill factor in the range of 0.7 to 0.82. So after fill factor, let's look at efficiency. So efficiency would be governed mostly by power output, by power input. So input here is coming from the solar radiation and output is coming from the solar cell. So efficiency is calculated as the ratio of maximum power output, that is Pmax, to the power of incident sunlight hitting the solar cell surface area. So efficiency would be Pmax upon power of incident sunlight. So Pmax, we have, like, in reality it will be, if we know the open circuit and short circuit, open circuit voltage and short circuit current multiplied by fill factor will give us the value of Pmax, and that is the power in. So the efficiency depends on the type of solar cell and the material or the technology that is used in respective solar cells. Most of the common ones, that is monocrystalline, polycrystalline and thin film, they have the efficiency ranging from 15 to 25%. As you can see here, monocrystalline N type 20 to 25. Lab efficiencies are much higher because there they are not subjected to the real world conditions. In real world conditions, the efficiencies would always be lower. So in commercial efficiency, 20 to 25. Polycrystalline, it's 15 to 18, and thin film is 17 to 19. Then there are some perovskite based, like tandem based solar cells, which have little higher efficiency than rest of the three, but then perovskite materials are much expensive than these crystalline silicon based cells. Then there are multi-junction solar cells which have been tested at lab scale at present with very high efficiencies reported up to 47-48%. Commercially, they have not been deployed yet, so we don't have the numbers for commercial efficiency. But again, so far as cost and construction is concerned, fabrication is concerned, it's very expensive for multi-junction at present. Now, with all those characteristics of solar PV cell, where we looked at IV and PV curve, fill factor and efficiency, let's look at how they are connected in series and parallel. All of you know the Ohm's law, right? V equal to IR, right? So voltage is proportional to current and constant of proportionality is called as resistance. And when we make a series connection, typically voltage increases, and when we make parallel connections, generally for an overall circuit, current would increase. So same logic applies in PV cells also. in series connection, whenever we need a higher voltage, we connect solar cells in series, and it is often used to match inverter or battery voltage so that the cable losses are reduced. And parallel connection is used whenever required voltage is already available but more power is needed. For example, when power comes to our house from the grid, the voltage is fixed 230 volt, right? In India, the value comes out to be 230 volt. So that voltage is fixed. Now, if we need more power, what we will have to do is to connect things in parallel so that more current passes through it and more power would be consumed. And for series, if the voltage, desired voltage is not reached, till that point the cells would be connected in series so that a desired voltage is reached, and then to increase the power further parallel connections can be considered, because once a desired voltage is reached and if it go on connecting cells in series, it will increase its voltage further. So there is no point in increasing the voltage further when desired voltage is reached. So on current and voltage curve for a single cell, if this is the IV curve, for series what will happen, the voltage will go on adding. So if for this cell voltage is V1, here it is V2, so voltage will be V1 plus V2. Similarly for parallel, the current will be added at constant voltage. But in large scale PV plants, we do not have only series connection or parallel connection, but we have a combination of those. So what happens in large PV plants, first all the modules, the solar PV modules, they are connected into series to form a PV string. So PV string is a series connected module, and then once the required voltage is achieved, multiple such strings can be connected in parallel to provide required current and overall required power output. Okay. The same thing which we discussed a few minutes back. So for large PV plants, the first thing is to go for a series connection, form PV strings, get the desired voltage, and once the desired voltage is obtained, you go for parallel connection to get desired current and power. Since PV cell is also like a battery or a two terminal device having one positive electrode, let us say anode, and one negative point, let us say cathode, and this solar cell, when it is arranged in the form of solar module or a panel, the connections are done electrically. Like if we have to connect PV panels in series, the positive of one module is connected to the negative of other module. Similarly, positive to negative is connected, and this positive and negative would be connected through the circuit or connected through the load or through the junction box. In parallel, if we have to connect in parallel, the similar polarities, the positives will be connected together to one positive, negative terminals would be connected together to one negative terminal. So that is how we connect in parallel. Now series parallel, if you have to do, there are two ways, whether you do connect positives together, negatives here, and connect them in series. So these two cells are in series, these are in series, and now this combination is in parallel with this combination because of positive and negative. Other ways, once we have this positive, negative, this vertical connection, so these two are in series now, and the combination of these two would come in parallel when we have positives and negatives connected separately. So this is the way PV panels are arranged in series parallel or series parallel depending on the plant capacity. Let us take one simple example to estimate or find out how many cells need to be connected in series or parallel or series parallel to achieve a desired voltage and current. Find the number of modules required for a PV plant that requires 240 volt and 40 ampere. So this is our voltage, that is our current. Each PV module is rated at 30 volt and 10 ampere. So that is the rating of single PV module. We need to find how many modules we would be requiring to satisfy this demand and how will they be connected. So, the first thing is series, then parallel, and then find the total modules, right. So, number of modules in series, how will you find them? What is the required voltage? 240 volt is the desired voltage. Voltage of one module is 30. So, we divide it by 30. So, how many modules we will get? 8 modules. So, we need to connect 8 modules in series to get the total voltage of 240, clear? So, number of modules in series would be required voltage by voltage of single module, that is 240 by 38. Now, the requirement of current is not satisfied because these 8 modules current is only 10 ampere. So, now to satisfy 40 ampere current demand with a 10 ampere module, how many PV modules will require? At least 4. So, we will need 4 modules in parallel to achieve 40 ampere because one module is able to give only 10 ampere. So, number of parallel strings would be required current by module current 40 by 10, which is 4. So, number of modules in series 8, number of modules in parallel, or the number of parallel strings of this 8 is 4. So, the total number of modules would be how much? One string has 8 modules, because once we connect these 8 modules M1, M2, M3, M4 up to M8, this is going to be one string. This one string is able to give us 240 volt and 10 ampere. Now, if we have 4 such strings, okay, and connect them in parallel, voltage is going to stay same, but current will be added up to 40 ampere. So, total number of modules are going to be 8 into 4, 32. Understood? So, total number of PV modules, it is the number of modules in series and number of strings in series. So, parallel, it is not module, it is the strings that we are talking about. So, one string consists of 8 modules. So, 4 string consists of 32 modules. So, here you can see it will be repeated 8 modules in 4 rows, they will be able to give you 240 volt and 40 ampere. So, that is how you can estimate the number of PV modules required if you know the rating of that one PV module. If you know the rating in terms of voltage and current, you can also determine how they will be connected, how much modules will be in series and how much modules will be in parallel. Now, next point is types of solar PV panel. This is based on the material, like they are made. So, there are 3 types of solar panels, and the primary difference between these 3 types are the cost and efficiency, because the material is different. Even though all 3 can be silicon based, but silicon would be in different forms. In one it will be crystalline, in other it can be amorphous. In crystalline also it can be monocrystalline, where all the crystals of silicon are homogeneous. So, it will be very expensive to make a homogeneous crystal of silicon and then convert it into a solar panel, compared to a polycrystalline where heterogeneous crystals can exist. Amorphous, thin film, it is like flexible, good for curved surfaces, and they are not crystalline. So, you can see from the picture, monocrystalline, it looks like very good, like similar looking crystals with no gradients of shades or colors anywhere. Polycrystalline, you can see there is a gradient of color shades because of non-uniform crystalline structure. And thin film, it is like a thin amorphous film. So, based on the appearance or based on the definition, you can easily make out that monocrystalline cells are going to be most expensive and difficult to manufacture, but they will be having higher efficiency because they have uniform crystal structure across the entire panel, and they are often produced from silicon ingots, and those ingots are very expensive to manufacture. Polycrystalline panels, they have a unique speckled blue color, but it varies in shade with different areas of the panel. And this is because the silicon that is used in these panels is not homogeneous, it is heterogeneous. Some crystals are of different types, some crystals are of different structure. Thin film solar panels, they are cheaper but less efficient than monocrystalline or polycrystalline, and they have a shorter lifetime, but they have like varied uses. So that's the definition of 3 types of solar PV panels based on the material of on the panel, whether it's monocrystalline, polycrystalline or thin film. If we have to compare it on the basis of different features, you can first on the base of material. Monocrystalline is high purity single crystal lattice. Polycrystalline, multiple silicon fragments are melted together, and in amorphous it's a non-crystalline silicon layer on some other substrate. Appearance is uniform. This is fragmented blue color with gradient. Amorphous is also uniform black or gray. They can be flexible and they are thin. Efficiency, monocrystalline is highest, polycrystalline is somewhere between amorphous and monocrystalline. Price per watt, it is like reasonable for monocrystalline, lowest for polycrystalline and highest for amorphous thin film. Price per watt is like in a way indirectly proportional to the cost or the efficiency. So here the price for monocrystalline or polycrystalline is lower because of higher efficiency than amorphous thin film, and in thin film the price per watt is higher because of lower efficiency. The space requirement here is also related to efficiency. Because it is more efficient, the space requirement is low. Here it is medium and here is high. Durability, monocrystalline, they have longest durability followed by polycrystalline, and amorphous have shorter lifespan. And so far as use is concerned, monocrystalline is good for houses or remote locations or small roofs wherever we have like less amount of land or on the top of buildings. Polycrystalline is typically used for large scale ground based solar PV plants, and amorphous or thin film would be used for curved surfaces because of their non-crystalline nature, non-brittle nature, or building integrated PVs, because buildings may have like windows and curved walls, and so for them amorphous thin films are useful. Finally, the last point, that's the components of solar PV module or panel. What is it that entire PV panel made of? Like we often see the panel, it's like blackish or bluish in color with some aluminum frame, and there are a couple of boxes behind it, but there are so many minute elements. If we fragment it layer by layer, we can see there are numerous components in a single solar PV module. This is a picture which shows a typical solar PV module, and you can see starting from aluminum frame, then there is a tempered covered glass, and here is the stringed solar cell. Stringed solar cells means the cells having PV cells in series as well as in parallel, and then encapsulation foil, that's foil 1, that's foil 2, both are made from EVA, ethyl vinyl acetate. Then there is a back sheet, and then there is a junction box. So when all of these are assembled together and compacted using a silicon glue, they form a solar PV module. So solar cells are stringed together to form panels, and this involves soldering, encapsulating, mounting on a metal frame, etc. And the tempered glass, this is 3 to 4 mm thick, and it is this glass which protects the cells from harsh weather, dirt and dust. It is very transparent, so solar radiation can easily reach the panel. Not only tempered glass, but the encapsulation foil is also transparent. So EVA, ethylene vinyl acetate, this sheet is a highly transparent plastic layer which is used to encapsulate the cells. It's basically laminating the cells from top and bottom so that it protects the cell and holds them together after getting strinked. So there is a EVA sheet, EVA foil on top as well as bottom of the cell. Then there is a back sheet, which is the rearmost layer of the panel. It is mainly for providing mechanical protection and electrical insulation, and all these things are packed together using silicon glue acid. And then there is a junction box, which is the point where all the cables or wires are interconnected with the panels. Okay, it is at the back side of the panel. It's like a small black colored box which will have some wires coming out of it, which will be connected to the other parts of the solar PV system. Then if you like focus, zoom in onto the solar panel, you will see like inside the frame there is a metallic stream, which is nothing but a cross connector, and within the cell there would be thin lines of metallic aluminum or copper, which are called as bus bars. So in this solar cell, which is encapsulated, the between the frame and backsheet, placed on that entire panel itself, is a cross connector. It helps to connect the solar cells or solar panels with each other. So bus bar, it is a thin strip of aluminum or copper which is found between the cells in a solar panel. Okay, so this would be bus bar, and it's a job of the bus bar to separate solar cells and conduct direct current generated by each of the solar cells to the solar inverter. Then there is an inter or a cross connector which helps solar panels connect with one another, and silicon glue creates a strong bonds to hold all the components together so that they are, and silicon glue is resistant itself to chemicals, moisture, dust and weather conditions. So this is how a typical monocrystalline silicon based solar PV panel looks like. And the most common panels that you see on top of the houses or buildings, they use standard 6-inch square 60 cell panels. So there are 60 cells mounted on one module or one panel, and most of them commonly they are a 6-inch size, and commercial systems have slightly bigger, like bigger size solar cells, and number of cells in panel is also higher, like 72 cell panels. Those are used for commercial systems. So these are the most common which are in existence at present, but as mentioned earlier in the previous lecture, this size has gone all the way up to 210 mm, and the size, the capacity of one cell has also raised from 2 watt to up to 10 watt. The modern cells can, one cell can have up to 10 watt. So that was all for today's lecture. To summarize, we started with solar cell characteristics, where we studied PV and IV curves and looked at the concepts of fill factor and the efficiency of the solar cell, right? Then we discussed how different solar cells can be connected in series and parallel, and how do we make a decision. So the thumb rule is, first connect in series till you get the desired voltage. Once the desired voltage is achieved, those series string can be connected in parallel to achieve desired current, which will give us desired power. Okay. Then types of solar PV panels, we saw 3 types: monocrystalline, polycrystalline and amorphous thin film. This is the most expensive but most efficient. This is like somewhere in the middle, and this is least expensive but least efficient. And then we saw the differences between 3 types of panels based on different features. And finally, we looked at components of a single solar PV module or panel, where stringed solar cell is often encapsulated by EVA sheets. Then you have a tempered glass. Then we have front sheet and back sheet. and it's embedded in a aluminum frame. And then there is a junction box which has all the connectors. If you zoom in, you have the like the things like finger, bus bar, connectors, cross connectors. Okay, so those are the components of solar PV module. So I think that was all for today's lecture, and we will look into how do we design. Like first we'll see like what are different types of solar PV systems, and then since standalone solar PV systems are most common, we'll look at how do we design one. So with that, let's stop here. Thank you.